Hi guys, welcome to another video. So today we're going to be starting on the first chapter of the year 2 pure maths module. So the chapter we're looking at today is called the Algebraic Methods. And as usual, before we start the chapter, there's some check-up questions for you guys to do prior knowledge check. Oops, the first answer is here. But pause the video and have a go at this. Okay, so for 1b, it's difference of 2 squared. And for C, again, it is actually difference of 2 squared. Okay, so first 2a, you get x minus 3x plus 6 because the difference of 2 squared and the one at the bottom will cancel out, the x plus 3's. And for B, x plus 4 over 3x plus 1. For C, x plus 5, sorry, minus x plus 5 all over x plus 3. So here we can see it be even, it could be either here, and odd here. Okay, to prove a statement by contradiction, you need to follow these steps. Step 1, we assume the statement is false. Step 2, we use logical steps to show that this leads to an impossible outcome or one that contradicts the original statement. The statement that shows the original assumption is false is known as negation of the statement. So we're going to prove by contradiction that there is no greatest odd integer. So assumption that there is a greatest odd integer, n, we need to use logical steps to reach a contradiction statement or impossibility. We know that there is no greatest integer. So if n is an integer, then n plus 2 is also an integer. So n plus 2 must be greater than n. So n plus 2 equals to odd plus even equal odd. Odd plus even, we know equal odd. So n plus 2 would be an odd integer and is greater than n. Therefore, there is no greatest odd integer. So we always have to have a statement or a conclusion at the end. Let's look at another question. Prove by contradiction that if n squared is even, then n must be even. So assumption, there exists a number n such that n is odd, but n squared is even.
Yeah.
We need to use logical steps to reach the contradiction. So if n is odd, then it can be written as 2k plus 1.
Yeah.
Therefore, n squared would equal bracket 2k plus 1 squared,
Yeah.
which equals to 4k squared plus 4k plus 1. Now
Yeah.
if we just take 2 out from 4k squared plus 4k, so we get 2 bracket 2k squared plus 2k plus 1.
Yeah.
So n squared is odd, which contradicts the original statement that if n is odd, then n squared must be even. As you can see here, 2 lots of anything would be even, and if you add 1 to it, it would be odd. Let's look at this one. And this is a classic example of proof by contradiction. We're looking at square root. So proof by contradiction that square root of 2 is an irrational number. So the assumption here, square root of 2 is a rational number and can therefore be expressed as a over b. Because any rational number, recall, can be written as a fraction, a over b, with a fraction in its simplest form. So we say these are co-prime. We need to use logical steps to reach a contradiction. So square root of 2, let's say, equals to a over b.
Yep.
If we square both sides, then 2 is equal to a squared over b squared. We multiply by b squared, 2b squared is equal to a squared. This means that a squared is even. So therefore A must also be even. This means that A can be written as 2n, where n is a different integer.
Mm-hmm.
So if we replace A with 2n, we could say 2b squared is equal to 2n squared. So if we square both sides, 2b squared is equal to 4n squared.
Yeah.
So divided by 2, b squared is equal to 2n squared.
Mm-hmm.
This means that b squared is also even, so therefore b must be even. We just shown that both a and b are both even. So how does this contradict the original statement? Well, remember we started off by saying a over b is the simplified fraction, i.e. co-prime. So this is a contradiction. If a and b are both even, then we could simplify the fraction a over b. However, our assumption was a over b is fully simplified. What we showed contradicts this.
Yeah.
Okay, a legend has it that Pythagoras believed that roots can be written as rational numbers. A student proved him wrong, and so he had the student killed. Scary stuff. Proof by contradiction, there are infinitely many prime numbers.
Mm-hmm.
So assumption that there is a finite number of primes, with the largest being Pn, we need to use logical steps. So imagine we listed all prime numbers, P1 for the first prime, P2, second prime, and so on, all the way up to Pn.
Yeah.
A number capital N will exist exist which is created by multiplying all the primes up to Pn and then adding 1.
Yeah.
So P1 times P2 times P3 times all the way up to Pn. So this number will not be divisible by any of the primes since 1 has been added. So therefore this number must either be a prime or have a prime factor which is not the original list.
Mm-hmm.
Either way, the statement has been contradicted. Okay, so now what we're going to look at is multiplying and dividing algebraic fractions. So the rules for fractions, just like with numbers, same applies when you're doing with algebra. So if I said a half times 3/5, you would just say 3 over 10. You multiply numerators together and denominators together. So if we look at an algebraic fraction, here it's just going to be AC over BD. So if I have, let's say, a number like this, 3/5 times 5 over 9, we could cancel diagonally, okay, or we could just cancel down the fraction. Same would apply, if you were to write it like this, you cancel out diagonally 3/9, which is equal to a third. So you already seen this in GCSE, which is going to apply with algebra now. Okay, so when you're timesing fractions, we check diagonally to cancel them out. This gives us C over B. And then when we're looking at a fraction like this, which is what this is the difference of 2 squared. Okay, so if you just write this as x plus 1, x minus 1, we could see diagonally, we could cancel these out. So when we simplify, we get 3 over 2x minus 1. So now when it comes to dividing, so 5 over 6 divided 1 over 3, for dividing, you change the divider into times and you flip the fraction around. Okay, so we flip, and we change. So same will go for algebraic fractions. So a over b divides a over c. It's going to be a over b times c over a. And again, diagonally cancel out, so we'll give you c over b. So now let's have a look at this one here. So we've got a quadratic here at the top, sorry, at the bottom. So the first fraction we leave, we change, and then we flip.
Yeah.
And now what we see for the numerator on the second fraction is the difference of 2 squared.
Yeah.
So we can factorize that. We can also factorize the denominator by taking common factor 3 out.
Yeah.
And x plus 2 and x plus 2 will cancel out. And the x plus 4 and one of these x plus 4 will cancel out. So that will leave you with just x minus 4 all over 3. So if we look at adding fractions, we know you need, with the numbers, we need a common denominator, and then you just simply add the numerator. So when we have an algebraic fraction, so 1 over x plus b, we could write this as 1 over x plus b over 1, and the common denominator would be x. So we multiply top and the bottom of b by x. So now we have a plus bx all over x. Okay, so now let's have a look at this one. We're adding this fraction. So the common denominator, we know before we get x plus 1, we can see there's a difference of 2 squared. So if we factorize this, the common denominator will be x plus 1, x minus 1. So the first fraction, we're going to times top and the bottom by x minus 1. So now we have a common denominator. We could just deal with the numerator, and we get the following. And then we could tidy that up. So that gives us 7x minus 3 all over x plus 1, x minus 1. Okay, so here's another fraction. What we're going to do, we want to split these up. So algebraic fraction is going to be very important when it comes to integrating or binomial expansion later in the course. So this can be written in that form. All this time you've been learning how to simplify fraction by giving it a common denominator, but now we want to do the opposite. We want to extrapolate that and write it as, you know, different sets of fractions. So we split them up.
Yeah.
So now what we're going to do, let's say if we have a fraction like this, 6x minus 2 over x minus 3x plus 1. So this has been tidied up from somewhere. What we want to do is we want to write these as separate fractions. So we know this came from 2 fractions, but we just don't know what the a on the numerator and b on the other numerator is. So we'll just call it a over x minus 3 plus b over x plus 1. Now the aim is to work out what a and b is. So we go back to our original question, you know, how do you add fraction? Well, you need a common denominator. So we could multiply a with x plus 1, because the common denominator is going to be x minus 3 and x plus 1.
Yeah.
B doesn't have x minus 3, so we're going to times top on the bottom by x minus 3. Now we have a common denominator, we could just add the numerator. Okay, so now we said that this fraction is equal to that, and we could see that has a common denominator. So if we just times both sides by x minus 3x plus 1, the denominators will cancel out. So we could simply see 6x minus 2 is actually equal to a x plus 1 plus b x minus 3.
Yeah.
If we let x equal to minus 1, if we substitute that in, on the left hand side we'll have minus 8, and on the right hand side, x plus 1, this bracket will cancel out, leaving with minus 4b. So now we know b must be 2. Okay, so now we need to know how we can get rid of the next bracket. How can we eliminate b? Well, if x equals to 3, it will cancel this out, wouldn't it? But you have to substitute into both sides. So on the left hand side we'll get 16, on the right hand side we'll get 4a. So that means a must be 4.
Yeah.
So now we could write this fraction as partial fraction. We could say this is same as 4 over x minus 3 plus 2 over x plus 1. Okay, so now let's look at this one here. So this one, we could write this, because this x cubed, we could write this as a over x plus b over x minus 1 plus c over 2x plus 1.
Yeah.
Okay, so now we need to think about common denominator. Well, the common denominator is x minus 1, 2x plus 1. So what does a need? A needs x minus 1 and a needs 2x plus 1. So we need to times the top and the bottom of a by this.
Yeah.
B needs x and he also needs 2x plus 1.
Yeah.
So everything in red you can see is what we need to make a common denominator. C needs x and he needs x minus 1.
Yeah.
So now you could see that all of this has a common denominator. So we could simply just add the numerator. So now we could just times, because this is equal to that, we have a common denominator. So if we times everything by the denominator, that cancels out. So 6x squared plus 5x minus 2 is equal to all of this.
Yeah.
So now we need to think about how could we eliminate one of these. So if we let x equal to 1, that will eliminate a, and it would also eliminate c. Can you see? Because if you put x with 1, that will go, this will go. So now you have to substitute in both places, left and right.
Yeah.
So once we work this out, we have 9 equal to 3b. So b is equal to 3.
Yeah.
Well, if we let x equal to 0, we could get rid of b and c. So if x equals to 0, we'll have minus 2 equal to minus a. So a is just equal to 2. So here, if we let x equal to minus half, that will get rid of a, because 2 times minus half plus 1, that bracket will be 0. We'll get rid of b as well, and so you leave with c. So substitute that in and work out what c is. So if we let x equals to minus 0.5, we get minus 3 on the left hand side, 0.75c on the right hand side. So if we work this out, that will give us c equals to minus 4. So now we have a, b, and c. We could just substitute it back in here and say this fraction can be written as 2 over x plus 3 over x minus 1 minus, because c was negative, minus 4 over 2x plus 1. So this one is slightly different in the sense we've got a repeated root in the denominator. So when we have a repeated root in the denominator, we could write this as a over x plus 1 plus b over x minus 5 plus c over x minus 5 squared.
Yeah.
You cannot write this, and this is a common mistake, you cannot write this as b over x minus 5 plus c over x minus 5, because this is a repeated root. You have to write one with the square and one without the square.
Yeah.
So now, bear it in mind, let's have a go at this question. So if we split this up, it's going to be a over x plus 1 plus b over x plus 1 squared plus c over 2x plus 1. So now, to get common denominator, a will need x plus 1, another one, because we need repeated x plus 1 squared, and it also needs 2x plus 1. B just needs 2x plus 1, and C just needs x plus 1 squared.
Yeah.
Now we have a common denominator. If we group them up, we see that the original equation and this partial fraction, the common denominator is the same. So if we times it by that, we're left over just numerator.
Yeah.
So if we let x equal to minus 1,
Yeah.
that will give us b equal to minus 2.
Yeah.
So if we replace x with minus half, we get c equal to 3. So the next bit here is you can't substitute anything in that will eliminate, just one and not the other. So we're out of ideas in that sense. So we have a little trick up our sleeve with these repeated roots. And what we could do, we could just say, well, let x equal to something else, because we know what b and c is. And the obvious thing to do is let x equal to, for example, 0. So if you let x equal to 0, you will have 5 equal to 1a plus 1b plus 1c. But because we already know what b and c is, we could just substitute that in. And then we could work out what a is. So a is equal to 4. So we could write this as a fraction, 4 over x plus 1 minus 2 over x plus 1 squared plus 3 over 2x plus 1. If you have an improper fraction, it must be first converted into mixed fraction before you can express it into a partial fraction. You can solve these kinds of problems by using algebraic long division, or alternatively you could do the identity method. So we know f of x would equal to q of x times the divisor plus some remainder. So 37 would be 12 times 3 plus 1. So if we have something like this, given that x cubed plus x squared minus 7 over x minus 3, we know it would be identical to this because you're dividing a cubic by a linear, so you'll get quadratic plus some sort of remainder left over. And in this case, it would be d over x minus 3, just like what you do with numbers. So what we're going to do, we're going to answer this question using long algebraic division. So we want to divide x cubed plus x squared minus 7 by x minus 3. So once we carry out the long division here, we know we'll get x cubed minus 3x squared if we divide all of this by x minus 3. So we do x squared at the top, and then we subtract the 2, so we get the following. So we have a remainder of 12x minus 7. Now you would have learned more of this in the AES maths. So what we say is we got another remainder. We could multiply with another 12. So 12 times x minus 3, so 12x minus 36. Now if you take them away, minus 7 minus 36 equals to 29. So a remainder would be 29. So what we could say is x cubed plus x squared minus 7 all over x minus 3 is identical to x squared plus 4x plus 12, remainder 29. So we could alternatively write this as x squared plus 4x plus 12 plus 29 over x minus 3. Okay, so let's have a look at this quartic one. We know this quartic can be product of two quadratic plus some sort of remainder. We want to find the values of a, b, c, d, and e. So if we compare the x to the power of 4 coefficient here, so x to the 4 would equal to ax to the power of 4. This is the only x to the 4 we will have. So in this case, a would equal to 1. So if we update this, we get the following information. So we could say this quartic can be written as the product of two quadratic plus some remainder. Now if we compare the x cubed term, x cubed could come from x squared times 2x, or it could come from bx times x squared. So these are your alternatives. So x cubed would equal to 2x cubed plus bx cubed. So b would equal to negative 1. So if we do the same with the x squared term, we know the only way we could get this is x squared times the constant, or c times the x squared. So doing the similar thing here, or there's another version as well, you can do cx squared or minus 3x squared minus 2x squared, and on the left hand side the x squared term is actually 0, so c would equal to 5. Now we know what a, b, c is. We could just look at the x term. So the way you could get x term is in the following ways. And on the left hand side we have 1x. So we could just write d is equal to minus 12. So now we're going to just compare the constant term. So minus 10 from here. And then from right hand side we'll have two versions. We'll have the minus 15 and then plus the e. So e would equal to 5.
Yeah.
So now with all the coefficient, we could simply say this quartic is actually this quadratic with the following remainder. Alright guys, so here's a past exam question from the legacy paper. So pause the video and have a go at this. This is worth 4 marks, so we'll say about 5 minutes. So you guys have a go at this question. Find the constant A, B, C, D and E. Okay, so here are the values. You could either do the identity method or long division. Either way, the value should be A is 3, B minus 2, C 7, D minus 8, E equal to 21. Okay, so moving on, we could split an improper fraction into partial fractions. So we know we need to divide the numerator by the denominator first to find the whole part. So 22 over 35, we could write this as 5th plus 3/7. Irregular fraction being split into two components, or we could write it like this. So we have a top-heavy improper fraction, we'll have a whole number part before the fraction. So we understand this with normal numerical values. So same principle applies for algebraic fractions. So here we know this is when we have x squared at the top and x squared at the bottom, we say this is still an improper fraction. So if the higher degree of polynomial at the bottom is same or more at the top, then we say it's improper fraction. So for example, if you had x cubed at the top and you had x cubed at the bottom, it's improper. If you have x cubed at the top and you have x squared at the bottom, it's improper.
Yeah.
So now, because this is an improper fraction, if we multiply out the bottom bit, the denominator, we get the following. We could use long division and work that out. So we only expect one constant value at the top of the fraction. So we have 6x minus 8. So now we know that this must be 3 whole plus some fraction. And what is this fraction? Well, that's a 6 minus 8, the remainder. So with 3 plus 6x minus 8 all over x minus 1, x minus 2. So we could say the 6x minus 8 over x minus 1, x plus 2. We could split this up as a partial fraction like we did in the previous slide. So we'll say a over x minus 1 plus b over x minus 2. And now we know we need the common denominator. The common denominator being x minus 1, x minus 2. So a needs x minus 2, b needs x minus 1. So we could work these values out later. So what we do from here, we want to equate 6x minus 8 to a x minus 2 plus b x minus 1. So once we work this out by laying x equal to 2, on the left hand side we'll have 4, and on the right hand side we'll just have b. So b is equal to 4. If we want to get rid of b, we lay x equals to 1. So on the left hand side we'll have minus 2, on the right hand side we'll minus a, so a equal to 2. Now it's all solved. We could write this as 3 plus 2 over x minus 1 plus 4 over x minus 2. Okay, so this is another exam question from the legacy paper. 4 marks, so pause this video, give yourself about 5 minutes and have a go at this. Split this up into partial fractions. Okay, so once we work this out, we could get the a value straight away because it's improper fraction. So a is equal to 3, b is equal to 2, and c equals to minus 1. So we could write this as a fraction, which is 3 plus 2 over x plus 2 minus 1 over 3x minus 1. Alright guys, thanks for watching this video. I'll see you next lesson.